In this video, I'm going to talk about the definite integral. In particular, I'm going to contrast the definite integral with areas under the curve that we talked about in the last video. I'm going to spoil the surprise that the difference essentially is that areas are always positive. They always take on a positive value because areas are heights and widths, and those are always positive measures, whereas definite integrals can take on negative values. So let's start off where we left off last time. Last time we had some function. This is our function f of x, and we split it up into n different rectangles, and we talked about how the width of each of these rectangles we were going to represent by a delta x, and that's exactly this total distance, which is b minus a, divided up into the n equal parts. And last time we said that we used the left endpoint to estimate the heights of each of these intervals, and we created a sum. And this time I want to say that although we used the left endpoint last time, we could have used any endpoint that we wanted. We could have used the right endpoint, we could have used the midpoint, and this is a generic notation that says that really I could use any point that I wanted in the middle of this interval as my, I'm going to call it, this is x1 star, because it's a point in the first interval, the first rectangle, and I could use the height of the function at that point to be able to estimate the height. Because as the number of rectangles increases, you see that these widths get smaller and smaller, and it means that the left endpoint approaches the value of the right endpoint because these things get squished. Last time we ended with this incredibly fancy notation to impress all of your friends and coworkers that we looked at the sum. This part is just telling me that I'm adding up all of the rectangles. I'm starting at the first rectangle and I'm going to the nth rectangle. And I know it's a rectangle because this part, the f of x star, is the height of the rectangle, and the delta x is the width of the rectangle. And we said that as our this gives us a number, right? And then we took the limit of these numbers, and each one of these sums has more and more and more rectangles. So we're not actually plugging in an infinity for n. What we're looking at is the limit as n approaches infinity for all of these sets of numbers. And we said that that's going to be equal to area, the area under a curve. And this is where I'm going to say that that is an oversimplification. And we were a little bit, I'm going to put a little star. And I'm going to say that that's equal to the area if the function f of x is greater than 0 and continuous. Meaning if we have some nice smooth curve, then we know that our rectangle heights are going to work out the way that we want them to. And we want this value to be an area value. It means that we can only consider positive heights, right? But this function might take on positive or negative values. And if it does, then that's exactly what we call our definite integral. So that leads me to my final definition, and it's the exact same definition as the above definition. But I say that my integral from a to b, whoops, let's scroll up a little bit so you can see this, of f of x dx is exactly equal to this definition of the sum. This is something that we call a Riemann integral. It's the limit as n approaches infinity of the sum from I equals 1 to n of f of x of I star. Again, these are the heights, delta x, this is the width, and that's my definition of a definite integral. I'll go ahead and put a box around it. What do each of these pieces mean? Let's break this down a little bit. So the first thing, you can see that some of these things are really similar to one another. The f of x is the name of the function, and really we can think of this as the height just as we thought of this as the height. These are both the heights of the rectangles. And the dx, rather than the delta x, is the width. Maybe I should put these in parentheses. Because this is the width as the limit of these sums has, well, I should say the limit as n goes to infinity gives me these dx's. It's really telling me what am I taking my integral with respect to. Finally, this notation over here says that I start at x equals a, and I end at x equals b. And you say, Carolyn, this looks a lot like what we did before with areas. And my answer is absolutely. So long as your function is continuous and greater than 0, these two things, this integral exactly computes the area from a to b. But if you have functions that dip negatively, something different happens. So that's my next example. Let's take a look at this function. So here's my function. We can call it f of x. And I want to know what is the integral from a to b of f of x dx. So this notation is telling me that I want to sum up all of the function values, because they could be positive or negative function values, along my x-axis. And in this case, we see that this is a continuous curve, and the curve is positive, and so that means that for this region of the graph, it really is just this area. But I want more than that, so this is some positive area. Here, I'm going to get negative height values. So this part is going to give me out some negative value under my curve, and this part will give me a positive value. So in an abusive notation, I could say that it's I'm going to put this in quotes and call it the area from A to B under the curve f of x. But we have to be careful, because we'll take this area, which is a positive area, and this area, we're going to count it as a negative area because these are negative heights. Again, that's an abusive notation because there's no such thing as a negative height, but there is such thing as a negative function value. And then this value would give us a positive value. So if I wanted to do a really basic example, let's do an example of the function. Let's let f of x equals sine x. So we know that this is our sine curve. And I want to look at the integral from 0 to pi. Maybe I'll go pi over to 2 pi of sine of x dx. So here's 0, here's pi, here's 2 pi. And I'm going to evaluate this graphically rather than algebraically. We're going to talk about algebraic techniques in the next section. But if I look at this, I see that for this part of the curve, it's continuous and it's above 0. So the integral from 0 to pi is just going to be this positive area. But the integral from pi to 2 pi is going to be this negative amount. And from what I know about sine curves, I know that they are symmetric, that this positive area is exactly equal to this, again, negative area, and it means that this part will cancel out this part. And my definite integral that starts at 0 and ends at 2 pi for this curve is going to be exactly equal to the number 0, because the positive value will cancel out the negative value. So next, let's look at a crazy example. This is an example of something that is not integrable. I'm not going to hold you accountable for this. This is just sort of some extra theory that I think is interesting and important. So this is a great counterexample of a function that I can't actually use integration on. So this function is called the Dirichlet function, and it's a function that's given as a piecewise function. Piecewise means that for certain conditions of x, the function is going to be 1, and for other conditions of x, the function is going to be 0. So if I were to draw a picture of this function, we see that the function is equal to 1 if x is a rational number. So rational numbers are things like a over b, where a and b are natural numbers. They're things that can be written as fractions. And There are a lot of numbers like that. I'm sure that you can name a whole bunch of them. So I'm going to start graphing that, right? It's all of these dots. But if x is irrational, such as pi or e, or any decimal approximation that doesn't repeat itself, then my function is going to be down here. Turns out there are a lot of these irrational numbers, even though we don't talk about them very often when we do mathematics. We like nice, easy rational numbers. So it's a bunch of dots down here and a bunch of dots up here. What if I were to think about integrating over this? Our definitions break down, because if I take, let's look at the integral from 0 to 4 of this crazy Dirichlet function. So here's where b equals 4. And I break it up into these n intervals. It makes a big difference whether I choose the right endpoint or the left endpoint or the midpoint. And as these intervals get smaller and smaller, for continuous functions, the right endpoint will always match up with the left endpoint. But for this crazy Dirichlet function, that's no longer going to be the case, because there are an infinite number of irrational points between rational points and an infinite number of rational points between irrational points. So depending upon what you choose, you might get crazy heighted rectangles. And there's no predictability, and that's why this is a type of function that doesn't work for Riemann integration. And you'll learn integration techniques if you do decide to go on and study analysis. I'm going to give you this preview of this cool function. So let's talk about what functions work. This is our definition. We find that the types of functions that are Riemann integrable, that we can do these integrals, are continuous functions, those are nice, or functions with a finite number of discontinuities. That means that, let's say I have one, and the limit has to exist. So let's say maybe at x equals 3, I have some sort of jump discontinuity. This is a continuous function. Jump, jump, goes straight for a little while. Let's say I have a removable discontinuity right here. You could imagine that my integral from 1 to 5 of this function, because it's all positive, I can approximate that by the area under the curve. And it doesn't matter that there's a little jump in it, right? I'm just going to break up the domain into the pieces. Maybe I can be technical. I could even break it up into 3 pieces and just sum the integral over this piece, over this piece, and this piece. And if I only have a finite number of discontinuities, I can sum up that a finite number of